talked about the minority carrier diffusion length, and we said that if you have a semiconductor with a doping density Nd and you shine light, you're creating electron hole pairs at x equal to 0, right? And then because the light is not really penetrating into the semiconductor, we said that this length was greater than the L absorption length on the light, that particular wavelength of light. Essentially, you're going to have an exponential decay in the carrier density. And we said we can define a minority carrier diffusion length LP. So this is what we have seen already, right? Now we want to represent that in a band diagram. What will we do? Okay. So to represent this, this sort of a minor decay in the carrier density, excess carrier density. How do we represent that? So, well, I mean, you can guess it already. You might have guessed, but anyway, let me go through the motions. So basically, I'll say my EF is going to be the same. Okay, I didn't change the problem. Point to EV. This is going to be EF, right? Now, let's say this is your X variation. Okay, so this is basically X equal to 0. At X equal to 0, let's assume that the carrier density is the same, 10 power 17, just for convenience. Okay, basically delta P at 0, let's assume that it is 10 power 17. Okay, so if your delta P was that, of course delta N also was that much, right? So basically, where will your Fermi levels be at X equal to 0? There will be at this point and this point, right? QFLs 0.42 EV away from EI. We have seen this in the last couple of slides back. Now, let's assume the carrier density, what should happen as x tends to infinity? Okay. So, or rather, we'll just act, when we are just reusing the concepts, right? As delta N, or rather, as delta N tends to 0 and delta P tends to 0, EFN tends to EF, and EFP tends to EF, right? That's what we have seen. So if you go far away, as x tends to infinity, let's say, the quasi Fermi levels should merge with EF. So I'll put as x tends to infinity. Okay, let's take just one more case at delta N, at some x, where delta N equal to 10 power 10 and delta P equal to 10 power 10. Because delta P is reducing exponentially, at some x you'll have this situation. What will happen? At this point, EFN is going to be equal to EF, but EFP equal to EI, because 10 power 10 is intrinsic carrier density. So Fermi level has to, the quasi Fermi level for holes has to be at EI. Okay. So at this point where this was happening, 10 power 10, and this will be almost here, right? This is at delta P equal to 10 power 10. Okay, EFP equal to EI. Please verify these things. Okay, so what we are seeing is the same thing. In the previous case, we saw that as it's approaching equilibrium, the quasi Fermi levels should move towards EF. So what should happen qualitatively is that this is the quasi Fermi level. As x increases, the quasi Fermi level should move towards EF. Similarly, the electron quasi Fermi level also should come towards the same point. Okay. So this is a conclusion. I mean, this is a qualitative, right? Qualitative analysis tells us that as x tends to infinity, sample approaches equilibrium. Hence, EFN and EFP should move towards EF. This is the conclusion, right, that we have made in this from the analysis here. So now let's try to do a qualitative calculation. I mean, you could actually do that. So this is still hand waving, right? I mean, we just put a few numbers that we want to have. We can actually introduce exponential decay into the expressions. So what was the definition of EFP? EI minus EFP is going to be KT ln of P by Ni, right? So that is going to be equal to KT ln of P was P naught plus, I'll put delta P at x equal to 0 exponential minus x by L P, right? Divided by Ni. Okay. Let me assume that the excess hole density is much higher than the equilibrium density. This is a low-level injection, and we saw that it is actually quite possible, or we said it will be possible. Assume delta P is greater than P naught, where significantly perturbing the minority carrier density, essentially, right? So if that happens, the above expression becomes KT ln of we can ignore the first P naught by Ni, so we'll simply put it as delta P 0 Ni into exponential minus x by Lp. Okay, this is the expression. So log A into B is log A plus B. So that's going to be KT ln of delta P of 0 divided by Ni and KT times ln of exponential. So this is going to be minus KT x by Lp. Okay. So you see what's happening is the distance. This was EI minus EFP. EI minus EFP is like a y equal to mx form. Mx plus C actually. So in the way we are writing C plus mx sort of. So this KT by Lp, this is the m, right? And C is going to be equal to what? 10 power 17. So 60 into 7. So that is going to be 0.42 eV. Okay. So 0.42 eV minus some slope. Lp we don't know what it is. Into x, right? So you can actually try to put in x equal to Lp and see what happens. Okay. Try to calculate it by the actual exponential and try to see by this approximation. Not approximation, approximation, because we said delta P is much greater than P naught. But at x equal to Lp, I think this will be true. Try to check it out, okay? Or it's the same order of magnitude, so you have to see that what happens. All right, please do that. Please try to put in and the numbers and check it out, so that you are confident. So what we are now saying is this exponential decay right here, exponential decay can be represented by a straight line on the band diagram. All right. So this is the conclusion of what is the analysis here. All right. So what I'll do is I'll pick up my EI when we have done it in the last slide. So essentially this is going to be your EFP. And this is EFP. You see, the quasi Fermi level for the electron is not really moving that much because it's a majority carriers, and we saw that the total density doesn't move so much, right? The minimum it can get to is a equilibrium majority carrier density, which is 10 power 15 in this case. Okay, it only changes by 2 orders of magnitude, whereas the whole density changes by 10 power, from 10 power 17 to up to 10 power 5. So 12 orders of magnitude. So you see that there is a large change in the minority carrier density, EF. Okay, that's why EF is changing by a significant amount. All right. So this is the concept of quasi Fermi levels, and we will actually analyze this, apply it next week, I believe, where we'll analyze the PN junction. We'll actually show you, or rather, when we talk of PN junctions in forward bias, we'll talk about it. Okay? Maybe the week after. All right. So this is going to be useful. So please practice some of these things that I mentioned. So There is also another advantage of using quasi Fermi levels. Okay, that is, we saw already that the current in the semiconductor, right, is consisting of the drift and the diffusion terms. These are the two terms that are contributing to the current, right? We have seen that in the last 2, 3 lectures we've seen this. So you see that quasi Fermi level now P is basically can be defined in terms of the quasi Fermi levels, right? So, and you have the dP by dx in the expression. So let's try to do that, So I wrote it as grad P. Essentially, grad P in one dimension is dP by dx. And that is going to be, I'll take a derivative of the carrier density. So basically, that's going to be Ni exponential EI minus EF E by KT. The whole thing remains as such because it's an exponential. And then there'll be 1 over KT times dEI by dx minus dEFN by dx. Okay. Remember, we said electric field is going to be 1 over q times dEI by dx. Okay. So we can substitute that into this expression. So this is going to be, I'll replace it by simply P times q by kt. dEI, I'll write it as q into E. So that's what is going to happen. Minus P into 1 over kt dE Fn by dx. Okay. This is a simplification, right? So now let us put it back into the current expression. So this we simply took the derivative of the carrier density. Let's put it back into the current expression. So Jp is going to be Qp mu P E electric field minus Q dP, and then the expression above, basically P times Q by KT E minus P to 1 by KT times dESN by dx. Okay. So I can expand it out. So basically this is going to be Qp mu P E minus Q dP Qp dP into Q by KT. So if you apply Einstein relationship, recall the Einstein relationship, this was mu. Okay. So we can substitute that. So essentially these two terms are going to cancel out, okay, because they're exactly equal. So what you're left with is plus Qp, or rather P to Q by KT times dP times, I'll represent it as grad EF. Okay. EF. And sorry, this should not be EFN. This should be, I made a mistake here. This should be not FN, but it should be EFP. And so this should be EFP. And so this should be EFP. And this should be EFP. Sorry, yeah, EFP, correct. So again, Einstein relationship will give you this to be P mu P grad of EFP. Okay. So what's happening is, if you're using quasi Fermi levels, we are able to represent the current densities Jp as simply P mu P gradient of quasi Fermi level. Jn, when I didn't show it, but Jn is going to be mu and n gradient of EFN. Okay. You will see quickly in the next weeks that when you have diffusion, drift, it becomes very difficult for us to keep track of what are the contributions to currents. Okay. So simply we can make our life easy by showing the currents as gradients of QFLs give the current density. That's it. Okay. So that's why quasi Fermi levels are very useful. Okay. So yeah, I mean, they have multiple applications and we will use them in the subsequent lectures. All right. So this essentially, uh, finishes the basic fundamentals that I want to cover.